Hello, Mr. Wheeler here. Today I'm going to be talking about kinetic molecular theory, root mean squared velocity, diffusion, effusion of gases, as well as the properties of real gases. First of all, the kinetic molecular theory, its purpose is to model gases as if they were acting ideal. So it's a set of assumptions that are required to assume a gas is ideal. And there are four basic tenets. The first tenet of the kinetic molecular theory, or KMT for short, is that particles are so small compared with the distance between them that the volume of the individual particles can be assumed to be negligible. So gas particles are so small and they are so high energy that they have very large spaces between them. And what this allows us to assume is that they will not interact, or their interactions will be negligible, so that we don't have to take into consideration intermolecular forces as well, nor collisions. The second part of the kinetic molecular theory is that particles are in constant motion. The collisions by the particles with the walls of the container that they're in cause the pressure exerted by the gas. So every time a gas particle strikes the outside of the container, it causes pressure. The third assumption is that particles are assumed to exert no forces on each other. They are assumed neither to attract nor repel each other. That kind of goes hand in hand with the first assumption, because they're just so far away from one another and there's so much space between them, they're not interacting. And then the fourth piece of this is that the average kinetic energy of a collection of gas particles is assumed to be directly proportional to the Kelvin temperature of the gas. So if the kinetic energy of the gas increases, so does the Kelvin temperature. If the kinetic energy decreases, then the Kelvin temperature is going to also decrease. And so the Kelvin temperature is actually just a measurement of the movement of particles. If you were to take a thermometer and you were to measure the temperature of a gas, like air, as the particles strike the glass of the thermometer, they're transferring their energy of motion, their kinetic energy, to the glass, and then those glass particles are going to start moving from that kinetic energy, and then that's going to cause the liquid inside the thermometer, whether it be an alcohol or mercury, it's going to cause those particles to continue to, or they're going to cause them to rise in kinetic energy. And if something rises in kinetic energy, it has a tendency to expand. And so the expansion of the liquid inside the thermometer is directly measuring the movement of particles where the thermometer is located. For the kinetic molecular theory, it's important to talk about root mean squared velocity. And what root mean squared velocity is it's just the average velocity of a gas particle. And if you were to analyze the movement of a gas particle, you're going to see something like this image over here on the right. There's going to be collisions all over the place. Collisions with the side of the container, collisions with other gas molecules. It's not going to be a nice orderly movement for that gas molecule. And so it's very hard to measure the velocity of that gas particle, especially because the velocity takes into consideration not only the magnitude of the speed, but also the direction. And so whenever you take a root mean squared velocity, it eliminates the factor for direction. And so looking at this top equation here, this is the equation for root mean squared velocity. And we represent the velocity of a particle by a lowercase u in chemistry. And so whenever we take the mean of something, we put a bar over the top, so that means the mean or the average velocity, and we square it, and then we take the square root. And then that's how we get the root mean squared, or the RMS velocity of a particle. That is equal to this equation over here, where we could substitute in 3RT, R being the universal gas constant. And this is not going to be your typical 0.08206 liter atmospheres per mole K, but instead we're going to be using 8.31451 joules per mole K. And what that allows us to do is it allows us to ultimately get a velocity in meters per second for this RMS value. So we have 3 RT in the top. T has to be in Kelvin to match up with the R value because it's joules per mole K, so K being Kelvin. And then on the bottom, the denominator of this equation, it's going to be the number of particles times the mass in kilograms. And so the number of particles is going to be measured in moles. And so we have moles of particles times kilograms. And what this ultimately comes out to be is the molar mass of particles in kilograms. So if you take the molar mass of, so let's say we're dealing with nitrogen. Nitrogen's molar mass is 14.01. Nitrogen doesn't exist in its monatomic state in the environment. It's going to be diatomic, so it's molecular N2. And so we have 14.01 times 2, that's going to be 28.02. That's grams per mole. Convert that to kilograms, it's going to be 0.028 kilograms per mole. And so that's what we're ultimately going to be plugging in the denominator here. And so we could simplify this equation to U RMS, or U sub RMS is going to be equal to the square root of 3RT over that kilogram molar mass value. If you look at a graph of the amount of nitrogen molecules, or any gas molecules you're talking about, versus the velocity, what you'll see is that as you increase the temperature, the velocity of the particles is also going to increase. And so if you look at these 3 temperatures, we have 273 Kelvin, 1273 Kelvin, and then 2273 Kelvin. Where the peak of each of these lines are is the average velocity of the particles at that temperature. And so you could see that you're going to have some particles that are higher than the average, some particles that are less than the average, but it's going to be a distribution so that the middle is going to be the average for the velocity of the particles. And so as we increase the velocity, you're going to see that the band is going to get more broad, but also that average velocity is going to increase. And so, as we would expect, if we raise the temperature of a gas, the velocity of the gas will also increase. And then, using the kinetic molecular theory, if you increase the velocity of the gas particles, then they're going to be colliding with the walls of the container harder, and then the pressure is also going to increase. So here's an example problem where we'd be calculating the root mean squared velocity of atoms in a sample of helium gas. And so it gives me the value as 25 degrees Celsius. Relative temperatures like Celsius and Fahrenheit are never good for gas calculations because those are they're relative temperatures and they can have negative values. So I want to immediately convert that to Kelvin. So 25 plus 273 is going to be equal to 298 Kelvin. If you want to be more precise, you would add 273.15 and you'd have 298.15 Kelvin. It's important to note that Kelvin does not have degrees, it's just units Kelvin. And so the next step is I want to find the molar mass of helium in kilograms. Because when I plug it into this equation, it's going to be in the denominator. R is always going to be the same, and then here we find the mass. So the molar mass of helium is going to be 4.00 grams per mole. I got that straight from my periodic table. Convert my grams to kilograms, and I'm going to find that the molar mass in kilograms per mole is going to be 4.00 times 10 to the 3rd kilograms per mole. You could put 0.004 kilograms per mole, but remember we want to be keeping sig figs, so we'd have to have 2 more zeros after it. And sometimes it's just easier to remember that if you just put times 10 to the negative 3rd after your standard molar mass, that's in grams per mole, you would effectively convert that to kilograms per mole. So now that we have our M value, our universal gas constant in joules per mole K, or in this case, Kelvin times moles, and our temperature, we could plug all of those in and solve for our root mean squared velocity. And so we have the 3, we plug in our R here, plug in the temperature, and then plug in our M value, and then once we solve, it will come out to be 1.36 times 10 to the 3rd meters per second. We gain a sig fig by adding the 273 here, so our temperature has 3 sig figs. The value that we used has 5 sig figs. And then our molar mass, we pulled 3 from the periodic table, so our answer should also have 3 sig figs as well. If you kind of check out the units, So we have joules per mole K for our R value, and then when we plug in our temperature of Kelvin, those cross off. And then on the top we have joules per mole. In the bottom we have kilograms per mole. So if we have moles in the denominator of the numerator and moles in the denominator of the denominator, those are going to cross off. And so over here it's going to be joules per kilogram. Joules are kilogram per meter, or joules are kilogram meter squared per second squared. And so that allows me to cross off kilograms, and then I get meters squared over second squared. But when I take the square root of that, I just get meters per second. And so that's where we get those units of meters per second. So that's why it's also important to make sure we're always using this 8.31451 joules per mole K rather than 0.08206 liter atmospheres per mole K. The difference between diffusion and effusion is subtle, and they have similar words, and they're oftentimes confused with one another. So you have to be careful when you're using these two words. Diffusion is when you have the mixing or spreading of gases. So whether if you have like a container of gas that you open in a room, maybe if I were to open up a cylinder of ammonia gas. Ammonia is a very pungent gas, and it's would burn your nose. So if I were to open that up in a large room, it would take a while before you as an observer, maybe sitting 50 feet away, would be able to detect that ammonia gas, because it's going to take some time to mix or diffuse through the air in the room. So that's what we're talking about when we're talking about diffusion. Effusion, on the other hand, is the movement of a gas through a small opening. And now when I say small opening, we're talking about pinhole size or even smaller. So an example of effusion would be if you've ever obtained a helium balloon from the store and you let it float around your house for a couple days. Over time, the helium is going to leak out of that balloon. Well, the way it's leaking out is through it's going right through the rubber of the balloon through the process of effusion. And so we could talk about diffusion rates, so how fast a gas can mix or spread, and we could also talk about effusion rates, how quickly a gas can move through a small opening. The one that has the equation is Graham's, or is effusion, where we have Graham's law of effusion. And Graham's law of effusion states that if we know the rate of the effusion of gas 1 and we know the rate of effusion for gas 2, actually, those are the things we would usually be solving for. If we knew the molar mass of gas 1 and 2, we could use this part of the equation over here, where we could take the square root of the molar mass of one gas divided by the square root of the molar mass of the other gas, and then we can get the relative rates of effusions for gas 1 and 2. And so a practical application would be to compare the rates of effusion for maybe helium and hydrogen. And so I would plug in the molar mass for helium as maybe gas 2. And so helium has a molar mass of 4, so the square root of 4 is obviously 2. And then I could plug in hydrogen, and then you'd have the square root of 1. So when you divide those two, you're going to get a 1 number value. But what that will give you is also the relative rates of effusion between the two gases. It's important to note that we have gas 1 on top on the left side, but we have gas 2 on top for the right side of this equation, and vice versa. So gas 2 on the bottom on the left, gas 2 matches with the molar mass on the diagonal on the top right of the equation here. And so here's an example problem. So calculate the ratio of the fusion rates of hydrogen gas and uranium hexafluoride, a gas used in the enrichment process to produce fuel for nuclear reactors. This figure refers to the textbook, Zumdahl Chemistry, 2007. So here's our Graham's law of effusion. So there's the equation. And so if we take the molar mass of uranium hexafluoride, it's going to be 352.02. The molar mass of hydrogen, which I mistakenly said on the previous slide was 1, but it's actually diatomic, so it's going to be 2.016. And I take the ratio of those, so 352.02 divided by 2.016, take the square root, I'm going to get 13.2. And so what this 13.2 value tells me is that hydrogen, a much smaller molecule than uranium hexafluoride, is going to be able to effuse through a small opening 13.2 times faster than our uranium hexafluoride. And so that's how this can be used. If you knew the rate of diffusion for one of these values, you could plug that in and then solve for the explicit rate of diffusion for uranium hexafluoride. But if you don't know that, you could have a comparative ratio between those two values. And then, yeah, so for sig figs, we could actually have another sig fig value here because we plugged in a molar mass for hydrogen to be 4 sig figs. So we could actually go one more sig fig here. A classic demonstration for diffusion, not effusion, is if you were to take a glass tube and you introduced hydrochloric acid. So what you do is you take just a cotton swab and you dip it in concentrated hydrochloric acid, and you take another cotton swab and you dip it in ammonium hydroxide, which is concentrated, or it's ammonia gas dissolved in water to its fullest extent. So if you dipped both those swabs in their corresponding solutions, and you plugged either side of the tube with those dipped swabs, you would then have hydrogen chloride gas start to come out of that solution that's saturating that cotton swab, and you'd have ammonia gas come out of that solution that's saturating that other cotton swab. And as those gases make their way through the tube at different rates, because they have different molar masses, these are different sized gas molecules, they will eventually meet, and then we'll have the reaction between ammonia gas and hydrogen chloride gas, and we will produce ammonium chloride, which is a white solid, and then we'll see this white band on the inside of the tube. And so that white band or that white ring on the inside of the tube shows us exactly where those two gases met. And we could back calculate and see what the relative rates between those two gases are, the rates of diffusion through the gas or through the air. And so we would use Graham's law of fusion. And so if you have, since the velocity is related to the distance traveled, and we introduce these two swabs on the either end of this tube simultaneously, we can eliminate the time factor. And so if we measure the distance traveled by the ammonia, so this pink band, and the distance traveled by the hydrogen chloride, this blue band, we could then get a ratio using their molar masses and find that's going to be 1.5. And so the distance traveled is going to be related to their molar masses through this law. But what we actually find is we don't actually get this value of 1.5. If we actually measure the distances, we actually get a value of close to 1.4. And what this shows us is that there are other things going on in this tube besides these gases just moving through the tube on their own. In fact, ammonia gas has a velocity of roughly 660 meters per second, and hydrogen chloride gas has a velocity of 450 meters per second at 25 degrees Celsius. And so if these gases traveled linearly from their cotton swab to their meeting point, at that rate, it would take less than a second for them to meet and react. However, if you've ever seen this reaction, if you introduce the swabs on either end of the tube, it takes quite some time, well over 10 minutes, for these to react. And what that shows us is that in order for these gases to diffuse or mix through the air in the tube, they have to undergo many collisions with other air molecules before they could actually meet. So the diffusion is significantly hindered by the air in the glass tube. If this was a vacuum, it would be a totally different case. When you compare real gases to ideal gases, which we can do using this type of graph. So if we were to graph PV divided by RT, so the pressure times volume divided by the universal gas constant and temperature, we would get we'd always have a value of 1.0 for an ideal gas if we graph that against pressure. So no matter what the pressure was, we'd have a value of 1 for that. But what we find is that all of these gases, in this case nitrogen, methane, hydrogen, carbon dioxide, they do not follow that 1.0 line, which suggests that these gases are not ideal except for when they are at a pressure of 0 atmospheres or one other pressure. But for most pressures, they do not act ideally. And so they're going to dip below ideality until a certain pressure, and then they're going to raise up above ideality. And then as you increase the pressure, they're just going to get farther and farther from ideality. If you were to do the same graph, but instead of changing the gas types, you just did it for, I think this is a graph for nitrogen, you'll see that the graph, the line goes closer to ideality as you raise the temperature. And so here we have the graph for, see how the nitrogen, the pink line over here, matches the blue line over here. We could see that this is nitrogen at 203 Kelvin, but as we increase the temperature from 203 Kelvin to 293 Kelvin, the line approaches that ideality line of 1.0, and if we raise the temperature even more to 673 Kelvin, then we get even closer to ideality. So what does this suggest? This suggests that gases will behave ideally when they are at a pressure of 0 atmospheres and when they have a very high temperature. And so if we kept on raising this temperature value, it'd approach ideality. So gases behave ideally at high pressures and low pressures and high temperatures. And the reason for is, if we go back many slides, the reason for that is because if we have gases at very low pressures, then they're not going to be crammed together and they're not going to be interacting with one another. And so that would satisfy tenets 1 and 3 of KMT, in that particles are assumed to exert no forces on each other because there's no pressure forcing them together, and the volume between the particles is very large and they're not interacting. And so low pressures, they behave ideally, and then high temperatures, they behave ideally. In order to correct a gas that is not behaving ideally, which has to be done a lot of the time, as you could see, for most pressures, except for when it's the pressure 0 or a specific pressure for a specific gas, or when we have realistic temperatures that are not extremely hot, we have to do a correction equation, which is called the van der Waals equation. And if you look at this equation, this is the ideal gas law, PV is equal to nRT, but it has some correction factors within it. So here's our P, here's our V, and then here's our N, R, and T. And then we have a correction factor for the pressure, and we have a correction factor for the volume. And so what we're actually correcting here is we're correcting for the amount of gas particles present or involved with the pressure. So as you can see, this is moles per volume, so that's a concentration. So if you look at this image over here, this would have a low concentration of gas molecules, and then for A, and then for B, we'd have a high concentration of gas molecules. And so all these gas molecules are having intermolecular forces with one another. And so you'll see that the red arrow for image A is going to be slightly bigger than the red arrow for image B. And what that is trying to show is that the velocity of this red particle in image A is going to be greater, therefore the pressure will be greater when it strikes this wall than it will be for B. And the reason why is because when we have extra gas particles around it, because the density is high, well, not the density, but the concentration of the gas particles is high, then these are kind of like reeling them in and not letting that gas particle strike as hard, because this gas particle has attraction, has affinity for the gas molecules around it. Whereas this one, when there's less gas molecules, it's striking that wall a lot harder because there's no intermolecular forces involved. And so that's what we're correcting for. So we're correcting for those intermolecular forces involved when a gas has a high concentration, and it needs to be corrected because it's close to the condensation point. So gases deviate from ideality when they're close to the condensation point, so high pressure, low temperature, and they also deviate from ideality when you are dealing with a very polar gas or a very large gas. And so those are all instances where we need this correction factor for the pressure, and it deals with the concentration. And so we have a van der Waals constant for That's what A is, and it's going to be different for every gas. So if you look over at this table here, you can see that we have a bunch of common gases and then their correction factor A. And the trend that you should see is that A increases as the intermolecular forces for those molecules increase. So as you probably know, water has the dual hydrogen bonds present because of the two lone pairs of electrons on the oxygen and the two hydrogens. So the two hydrogens bonded to the oxygen. And so between two water molecules, you have two hydrogen bonds present in every single case. And so we have a lot of intermolecular forces at play for water. Therefore, A has to be a lot larger of a value, and therefore more corrective than, say, something like helium, which doesn't have hydrogen bonding, which does not have dipole interactions. It just has van der Waals attractive forces. And so the greater the intermolecular forces, the more that pressure needs to be corrected in the ideal gas law. And so that's how the pressure gets corrected. The volume also is going to get corrected, because what we're correcting here is we're correcting for the actual volume of the particles. And so if a gas particle is very large, it's going to have a bigger correction factor than a gas particle that is very small. So if you look at our smallest gas, hydrogen, that's going to have the smallest correction factor of 0.0266, whereas some of our larger gases, such as chlorine gas, chlorine is a very large gas, is going to have a larger correction factor, because the only thing that we're correcting for is the volume, because we take that in consideration also with the pressure over here. So pressure is a concentration and a constant value correction, and then volume over here is just correcting for the volume of the particles. That's why it takes into consideration the number of particles present. So we're correcting P in that ideal gas law, we're correcting V in that ideal gas law, and then NR and T don't need corrected. And so to solve this, you'd plug in your volume here and here, plug in your moles here and here, find your correction values A and B for whatever gas you're dealing with, and then you could solve for, you would always have R, and then whether you're just solving for T or P, you could solve for one of those. That's it. Hope that's helpful.